I'm Denver Dash. I'm Director of Machine Learning at Occipital. And I'm going to talk about the combination of geometry and machine learning today. First, a quick overview of Occipital. We're a small team, about 50 people, 4 locations, San Francisco, Boulder, Gainesville, and 1 recently opened in Madrid, Spain. It's really a 3D computer vision perception company. We do hardware, software, and a lot of really cool guys that I've been working with lately, from Microsoft, from NASA, from Google, Google Tango project, and most recently I come from Magic Leap, where I led the hand tracking effort there. Okay, so in the past 10 years or so, 2 superheroes have emerged from computer vision research. 3D computer vision and deep learning, of course. And in this talk, I'm going to talk about these 2 approaches, compare and contrast them a bit. And I'm going to argue that now is really the time where combining these 2 approaches, it's really sort of the next frontier in computer vision. Is there a weird flicker every time I turn away? Okay. All right. Hopefully that fixed that. So the first superhero, geometric 3D vision. This has been a workhorse of computer vision for at least 5 years now. It's given us new sensors. It's given us just unprecedented ability to understand the world around us. And I'm really sorry about that flicker. Let me try this. All right. I'll just push through it. Hope it doesn't get more frequent. 3D depth estimation, dense reconstruction, 3D map acquisition, all this stuff has been made possible thanks to just 3D geometry, basically. We can track cameras very precisely with very low latency. And in cases where the tracking fails, we can rapidly relocalize in milliseconds on mobile devices. So this has been really critical to a lot of the progress in AR and VR, and a lot of other really cool applications. So our second superhero, of course, deep learning, has made, just in the past few years, stunning progress on a lot of computer vision problems that for a while, people were just resigned to thinking were never going to get solved, basically. So in 2015, was it 5? I can't even read it now. ResNet came on the scene and could solve image classification in better than human level performance. 2014, DeepFace allowed us to do human verification better than humans can do it. 2016, we could do speech recognition better than humans. And then 2017 showed just really impressive results on instance-based human articulated tracking. And very funny videos too, yeah. And then some of the most really impressive work has actually involved combining deep learning with established techniques such as reinforcement learning. And if you look at, for example, DeepQ learning and AlphaGo, these were programs that combined reinforcement learning with deep learning, and they can do, for example, Atari games better than humans, and of course, AlphaGo beat the world champion in Go in 2016. So these are cool examples of taking sort of deep learning and mixing it with a well-established, toolkit of techniques and doing something really super impressive that had never been done before. So we want to combine these 2 superheroes, and this could go a few different ways, right? You could ask, how can I improve 3D vision by adding deep learning to it? So the classic failure case for a lot of these 3D tracking and 3D computer vision cases is a textureless white room. Most geometry methods require the ability to find correspondences between points and two frames in an image. If you can't find any points, you can't find any correspondences. So this kind of just has a tendency to break a lot of 3D computer vision. On the other hand, what deep learning is really good at is understanding the world, what's in a 2D image really well. So here's an example of semantic segmentation being run on one of Occipital's data sets where we're scanning a room. And you can see you can do very dense pixel-wise classification of each pixel in the room. And you can imagine you could do a lot of stuff with that to mitigate this problem of a featureless room. You could look at corners, you could track objects instead of features. There's a lot that can be done to help there. So you could go the other way and you could say, well, is it possible that 3D vision techniques could actually help deep learning in some way? Deep learning is trying to understand the world, the semantics of the world. Can 3D vision help there? And I insist, yes, it can. And one good example is just the estimation of scale in an image. Now, you can do this with just a deep learning approach, and people have tried to do it. You can get an idea just based on the typical scale of objects, how big things, the typical scale of objects in your training data, for example, how big things are in a given image, such as this one. But you lose the precision that you would have with a 3D technique. If I were to ask you, even a human, if I were to ask a human, how big is that weird art statue in the background? Is it 130 centimeters, 150 centimeters? Humans would have a really hard time distinguishing exactly how tall that object was. Even worse, there's these extreme pathological cases that look nothing like the database that could totally throw off the estimate of a deep learning system. These 3D geometric methods, on the other hand, they are unfoolable in a sense. They use very precise information that humans kind of gloss over, but allow us to very precisely estimate things like scale. So we can also have hybrid approaches here. It's not just one approach helping the other. They can help each other in a sense. So here's one example of PlaneNet. This is a deep model that is designed to detect all the planes in a room, basically. So this is a very 3D computer vision type of task that is being tackled with a deep learning model almost exclusively. And you can see here, is that video running? Oh, there we go. Okay. So you can see it's not perfect. It does something. There's a plane there, and it recognizes some planes. There's a lot of junk, and things don't really line up very well. But if you just take this model and you add something from computer vision, namely some sparse depth, and use that as input into the network, you can retrain this network to improve a lot of the failures of the original network. It gives you a much better sense of scale. The wall meets where the floor is, and things are more like 90-degree angles. So again, this is again 3D vision helping with the scale problem, a deep learning model. So the big picture here is that deep learning is really good at doing things that humans can do really well, but humans are not the best at everything. They can be fooled. And the things that fool human are likely going to fool a deep learning model as well. You can see optical illusions and other kind of things. These things will be much harder to fool a geometric method. Okay, so one of the weaknesses of deep learning is that it really requires data, right? And this is also a weakness of 3D, because 3D requires a different kind of data than we're used to seeing and that most deep models have been trained on. But I want to make the point here that these success cases of deep learning, the ones that have really achieved superhuman performance, or at least human level performance, these are like a laundry list of the problems that we had really good data for. Either a lot of data or a lot of diversity of data, or in some cases had the ability to generate essentially infinite amount of data in the case of the game playing applications. So I want to make the point that, I'm sure we're all aware that data is an important part of the deep learning revolution, but I want to make the point that in order to really take a good model and make it like a human level model, data is the first 2 bits of that problem. Getting the right data is super, super important. And then again, so 3D data is harder to collect. Here's an example of PX80. This is a sensor that Occipital sells. It's a mobile LiDAR, mobile color LiDAR. And we did a scan of downtown Gainesville just by walking down the street holding this scanner. But you can see this data is much more complex than a bunch of images. It's messy. It doesn't fit into a convolutional neural network very easily. And while people are starting to tackle this problem with a few different methods, it's really a very, very understudied problem, how to deal with the 3D nature of data. And of course, just because there's more of it, requires much more extreme compute requirements. So academia has come to the rescue regarding this problem somewhat. There have been in the past few years a few cool new data sets that have 3D information and have full 3D labels. The most recent one is ScanNet. It's also the biggest one. Has 1,500 complete scans. Each voxel in that scan is labeled with semantic information. And just in the 1 year that this data set has been out, there's been many just really cutting edge new work that takes advantage of it. One of them is that plane net model that I showed you earlier, just being able to estimate planes in a room. This is based on the ScanNet data. So this is just starting to come online now. We're starting to get some good data sets to fuel this combination of these 2 approaches. So Occipital, we have a product called Canvas where users submit scans of their rooms to us, and we give them back CAD models, and we provide a service for them. And so we value, above all, the privacy and security of our customers' data. But we also recognize that this is a really potent source of variation that we can't get in these kind of academic data sets, which are mostly taken, on Stanford campuses where they have very uniform styles and administrative buildings all kind of look the same. So these have a set of variety that we can't get in those kind of data sets. So to balance these kind of two interests, one protecting the user's privacy and the other to make a data set available publicly for research, we're kind of exploring the option of letting users opt in to have their data released publicly. And we offer them a discount. And up till now, we've had about 700 people have opted in to let their 700 scans, rather, not people. Many people had multiple scans. So we have about 700 scans that we're kind of curating. And as you can see in these videos here, the variety is really pretty cool. You have like crazy Egyptian stylistic interiors. You have log cabin kind of interiors. You have exteriors, all different rooms. So this variety is what can really drive the ability of a deep model to generalize and to scale. So again, this is still in the early phases. We're not sure exactly how it's going to play out, but hopefully we can add some semantic labels to this and get something kind of like the ScanNet data set with much better variety and maybe even more total scans. Okay, so data sets are improving. A lot of other things are coming into place that make this combination really kind of compelling right now. Obviously, on-device compute is going up constantly. But more importantly, we're seeing specialized ASICs that are designed specifically for both 3D computer vision and deep learning. And of course, just the open nature of the deep learning community. Whenever a new model is developed, a new architecture is developed, it's almost immediately available to be used. And new frameworks and code just make this technology more accessible to, for example, 3D computer vision researchers. Okay, so what are some killer apps that might come out of this? Of course, no one can predict the real killer apps, but we have some ideas. And at AWE in San Francisco, we did a demo of this particular virtual reality kind of advanced perception for AR/VR scenario. Here we have a user with a virtual reality headset, and there's no lighthouse, there's no room setup. It's basically just some cameras that are mounted on the headset, and using the cameras, we track the user's head pose, and then using cameras, we also just understand the world around us so we can allow them to get immersed in a virtual world, and we can provide collision avoidance and all the things that you can do with sort of a room setup scenario now. We just could do automatically just by strapping on the headset and going, essentially. So this particular demo was pure computer vision. There was no deep learning involved. But we could take this idea further. We just want to take a single camera, or maybe a couple set of cameras, do a quick scan around a room, and we want to understand the room as much as we can. And so here's an example of monocular dense reconstruction that we can do by combining some elements of deep learning with some elements of classical 3D vision. And you can see the room is not perfect. It's still a little rough, but we're doing stuff that up till now could really only be done with a dense depth camera, which requires a lot more power, a lot more space. And so it's pretty cool that we can see that we can actually start to do dense reconstruction with just a monocular camera. So another interesting application involving AR/VR, a person is sitting in their furniture in their home, and they're in some virtual world, and we want to basically put their furniture into the virtual reality experience, right? Furniture, or the objects around them, more generally speaking. So if their cat or a person walks through, they can be made aware of them in their virtual reality experience, even possibly, rigged up as a dragon. You can rig up your cat as a dragon and really make them an immersive part of the experience. So having a good understanding of the world around you would enable something like this. And the starting point really is just furniture. If we can solve furniture first, then we can move on to people and pets and all that stuff. So to solve the problem with furniture, the formulation is you have some kind of 3D reconstruction of the world, and then you use some deep learning model to semantically segment that space. Then you can pull out the segments that correspond to the furniture of interest that you want to try and either incorporate into virtual reality, or this can also be used for things like interior design. You can take out furniture and put in new virtual furniture. And then we need to then, given that extracted object mesh, find a CAD model that kind of matches its geometry, and then scale and align that CAD model onto the object. And so we've begun this process. At the top here, you can see some results for the retrieval aspect of it. We have some kind of pre-segmented chunks of mesh. There's 2 chairs there. And did I have a pointer here? And then you can see the top 5 CAD models that are retrieved based on that chunked mesh. And then at the bottom, here's the full pipeline. Aside from that alignment part, we start with a 3D reconstruction. We do semantic segmentation, object mesh. So this is all one example of a successful retrieval for a chair in this scene. Yeah. So we're getting there. It's not done yet. We're on the road. We're heading someplace we hope is cool, and because of all of there's this abrupt sort of unblocking of a lot of computer vision problems that deep learning has provided. There's a lot of things we can try. Together with the sort of maturity of the toolkit of 3D computer vision, there's a lot of ways these things can go together. So actually a lot of different roads you can take. So we're heading down that path. We're letting the research and the data and the market kind of tell us where the best way to go is. And hopefully we will be somewhere this road will lead us to something that's even better than human spatial computing, some superhuman kind of spatial computing. All right, so if anyone wants to get started in some of the 3D aspects of what we do, we have some SDKs that are readily available. Structure SDK goes along with our structure sensor, 3D sensor. Bridge SDK is our SDK that goes with our bridge device, which lets you do mixed reality on Mac OS. And then finally, we have this Occipital tracking SDK, which goes along with our new sensor, Structure Core. Still called Structure Core, okay. And it's cross-platform, and it's also occipital tracking can be used with other sensors besides our own sensor. So, okay, so that's it. Anyone out there who's interested in looking at this kind of stuff, we're definitely hiring and looking for interns, looking for full-time engineers. Send an email to jobs@Occipital.
Are there any questions?
Yeah?
Oh.
Good.
What?
There you go.
It's working? Okay. I have a question. Do you use the semantic of the objects in relation to each other? For example, you have a scan of a table or something, yeah, and we have 4 chairs around of them, and one is very good explained, and the other one not, with their points, yeah.
Yeah.
Because of that, but it's very common that we have 4 similar chairs around the table,
Yeah.
or an ashtray that you detect an ashtray on a table,
Yeah.
not on a floor.
This is all very possible. We don't do that currently. That would be sort of a joint, basically, instead of doing a sort of chunk of a mesh at a time, you want to do the whole mesh together. And so, there's a lot of work sort of in the early 2000s in graphical models where they did joint estimation of objects and stuff using graphical models and stuff like that. Yeah, but that's definitely a possibility. If you can't do it independently, that's bound to help somewhat, yeah.
Anybody else? Denver, thank you so much. That was a great talk.
Yeah.